Hello everyone, and today I want to discuss a very important concept called stoichiometry. Let's start with take a look at typical chemical reactions. We call it chemical changes. Here's one very simple one: hydrogen gas mixed with oxygen gas will produce water when ignited, and you can come and going into detailed description. Generally, this is a sentence or two to describe a chemical change. And here we encounter some issues. The first one will be the language. Okay, so the First one will be the language. As I speak English now, and this is a description for the chemical reactions. But if you move on to the other language like Russian, Japanese, Chinese, Korean, all the descriptions will be different, especially the names for the molecules, for the compounds involved in the chemical reactions. And second, so those descriptions are lengthy and really cumbersome, and they really kind of hard to handle. So we scientists, we kind of easily trying to find an easy way out, and we're trying to do a universally accepted system in describing chemical changes. And here comes that the big periodic table, and that table, we call it the periodic table of elements. It's universally accepted. Those are the ones for universally accepted symbols. So for instance, hydrogen gas, if you go out and indicating this is H2 with the symbol, the G in the parentheses describing as hydrogen gas, anywhere on the planet, if the person is properly trained in chemistry, will understand exactly what kind of molecule you're referring to. Hence also the oxygen gas in this case, and water vapor in this case. So now we actually can get on the path to start writing down something that would be universally accepted, and in this case we can shorten the representation for the chemical reaction from the particular description, the sentence description, to this, what we call it skeleton equation. You will learn much more detail later on when we talk about the type of chemical reactions and chemical equations, and actually how you balance the chemical equations. So this is actually based on two things. Its first one is law of conservation of mass. As the law of conservation of mass, you probably started learning in elementary school days or maybe in the middle school days. It states the matter cannot be created nor destroyed during a chemical or physical change. So the matter is constant. The mass matter cannot be created nor destroyed during chemical or physical changes. It is important to understand, actually, you have a context for the law of conservation of mass to work. It's only applied for the physical and chemical changes, but if later on you learn that if we actually, in the nuclear reaction, when we change the nucleus, this law does not hold. The other thing is, the other observation we have here over the years is no nuclear reaction, which means no change in identity of the elements happen in chemical reactions. Chemical or physical changes. Okay, so A and B combined will give you the conclusion is number of atoms has to be constant. So which means how many, for any given element, how many of those elements you start with before the chemical reaction takes place has to equal to the number of that particular element after the chemical reactions. So this one will lead to balanced chemical equations. Okay, in this case, let's examine this hydrogen and oxygen gas reaction. Hydrogen and oxygen gas reaction gives you water vapor. Okay, gives you water vapor. And you now notice you have two hydrogens on the reactant side, two hydrogens on the product side. Good. You have two oxygen atoms on the reactant side, but only one on the product side. Now we have a problem, and we need to get it balanced to abide by those 2 points: law of conservation of mass, and there's no new elements created nor the old elements destroyed, which means translated into changing in the nucleus that or changing in identity of the element. So what we use later on, you can learn in detail, is use this adjusting what we call the coefficients. And this one's by default we have 1 and 1. We do not write those by default in front of the molecules. So in this case, you have two this one's you have 2 here. So you have 4 hydrogens, you have 4 hydrogens, you have 2 oxygens, you have 2 oxygens. So this is a balanced chemical equations. This is a balanced chemical equation that abides to the 2 points mentioned on these slides. And here comes a very important applications for the balanced chemical equations. In this case, let's reproduce that. 2 hydrogen gas molecules will react with 1 oxygen gas molecules to produce 2 water molecules, and in this case water vapor. Okay, so then we are going to get into what we call the stoichiometry. Try to pronounce that 3 times in a row. Stoichiometry, stoichiometry, stoichiometry. It's a Greek word, and it's derived from stoichi, means counting, ometry means element. Okay, it's just counting elements. And in this case, it is very, very important, as I said before, is 2 hydrogen molecules will reacts with exactly 1 oxygen molecules to produce exactly 2 water molecules. Oh, so if you extended this out, you will have 2 moles of hydrogen will be equivalent to 1 mole of oxygen will be equivalent to 2 mole of water. And that is the crucial point in the discussion of stoichiometry. So when we write this first, it's mole equivalency, the mole equivalence is only applicable to the above balanced chemical equations. It only applies to this particular one. Hydrogen, 2 hydrogen plus 1 oxygen molecule will produce 2 water molecule. It's B. Those numbers directly correlates with coefficients in the balanced chemical equations. Okay, so as you can see here, the format is getting a little bit similar, because this is where we're going to have a discussion on switching between reactants and the products. This is also the ones looking at it how related to the stoichiometry. Stoichiometry is started to study the relationship between chemicals when they are undergoing a chemical reaction. So by using that, and also obviously the factor labeling method, let's take an example looking at this. The question is asked, how many moles of water will be produced when 0.24 moles of oxygen gas is reacted with the excess of hydrogen gas? As we can see in this case, and we're still referring to that particular chemical change or chemical equations, we should have balanced the chemical equation. 2 hydrogen gas molecules will react with exactly 1 oxygen gas molecules will generate 2 water molecules. In this case, we have, let's write it again, 1 mole of H2 is equivalent, 2 moles of H2 is equivalent to 1 mole of O2 is equivalent to the 2 mole of H2O. So now take a look at the detail of the question. When you started with 0.24 mole of oxygen. What do you want to get? You want to get moles of water. So you want to get moles of water. And yeah, it's okay. So it's actually have to cancel more of oxygen has to come here. So now you just directly, just as every factor labeling approach will be, you will see 1 mole of oxygen equals 2 mole is equivalent to 2 moles of H2O, and you cancel this. And remember, this term has to equal to 1 because it's a conversion factor. So this one is 0.48 mole of H2O will be produced. Okay. After that, so actually I want to put it together, and let's using a little bit abstract approach, and I'll give you a very generalized balanced chemical equations. You have A of A plus B of reactant B will give you C of product C plus D of product D. The A, the big letter A, B, C, and the D identifies It is actually the formula for the compounds or the atoms or the ionic compounds. That is part of the reaction system. The A and B are reactants, C and D are products. So small letters A, small letters A, B, C, and D is referring to as coefficients, reaction coefficients. Okay, so those are the coefficients. Very important. A mole relationship equivalency is in A mole of A is equivalent to B mole of B is equivalent to C mole of C is equivalent to D mole of D. Very important equivalency relationship, all based on balanced chemical equation shown above. And also remember, as we discussed before, for the matter A, we have 4 perspective triangles. You recall this logic map, right? For this one will be number of particles. It's also A. You have 6.022 times 10 to the 23rd Avogadro's number to contend with. This one will be mass of A. That will be in grams. There will be the molar mass. Okay, so this one will be the solution volume will be in liters. This is molarity. And if A is a gas, so then will be gas volume STP, and obviously it's in liters. There will be 22.4 liters. So all this will be referred to as A solution volume, solution A. So it's the mass is A. So for this is actually the centralized link between those unique properties are moles. Similarly, you will have mole B, and I'm not going to repeat that due to time constraints. You're going to have those 4 triangles exclusively describing the substance B. So now you have mole C. You also have those 4 triangles exclusively referring to C, and then you also have for mole D, and it's like a broken record now. You have these 4 triangles, and now how they are linked together is actually they linked through this relationship. They link through this relationship of the stoichiometry, the foundation of the stoichiometry, that it will be the balanced chemical equation. And now you actually have the means for going from any corner like this. If I want to use mass of A, actually calculate particle number of D. Here's the path you go through. Here's the path you go through. Okay, so you go to the mass, go to the mole of A. You take mole of A, going down onto this relationship. You take A, mole of A, convert it to mole of D. You take mole of D right into here and go into the number of particles. This is the logic map for reaction stoichiometry. So I want you to pause here and start think about it for 2 or 3 minutes. I really want to get to the essence of it. This gives you the logic steps it takes to solve rather complicated, complex stoichiometry problems. And let's now take a look at an example. So now the question, we're referring to the same chemical change, chemical reaction, the reaction between a hydrogen gas and an oxygen gas. Now we're asking is how many hydrogen gas molecules you need to produce 36.0 grams of water. To do that, so now you see, let's rewrite the balanced chemical equations. It will be 2 hydrogen gas plus 1 oxygen gas will give you 2 water molecules. And now we started with 36.0 grams of water, but now we want to switch to molecules of hydrogen gas, H2. Okay, so you're going to say I'm going to cancel it, the water and grams of water, switch it to mole of water. So this is not what I want. So mole of water, and this is, you notice this is the brackets being shifted. You shift it at the mole, and now you have the mole of H2, you have the molecules of H2. So in this case, then you come in to fill in the blanks. 1 mole of H2O will be equal to 18 grams of H2O, because you have 2 H, each one is 1 O, oxygen is 16, so it's 18. You have 2 moles of water is equivalent to 2 moles of hydrogen, and now you have 1 mole of hydrogen is equivalent to 6.022 times 10 to the 23rd times 10 to the 23rd. And now you can actually cancel those units and get what you wanted. Simply plug in and do the math, and you will have 1.20 times 10 to the 24th molecules of H2. Let me double check whether that's correct. This is cancelled, and this one will give you 2, and 2 times 6.022 is 12.044. Yeah, that's correct, due to consideration for the sig fig. So it's 1.20 times 10 to the 24 molecules of H2. So here again, use the factor labeling method, but now we're switching between any compounds or the element that's part of the balanced chemical equation. This is the use of stoichiometry. So to summarize, we learned the balanced chemical equation is the true representation of any chemical change, and we can actually utilize that. To calculate the relative amount of any substances involved in the chemical reactions. So with that, the Volcast draws to an end, and you should go to the corresponding worksheets and look at try it out, and then double check with the answers. Thank you very much for your attention.